As I mentioned, I'm talking to you from our business, Build Equinox, and we'll talk a little bit about our facility here because it is a net zero business powered with 8 kilowatts of solar PV. And we'll talk a bit about this house, my house, that we call Equinox House, which was built in 2010 and is a zero plus home, enough solar to power the 2 electric cars that you see in the garage for driving about 8,000 miles a year. And I hope overall that what you'll find from this is that throughout North America and certainly beyond, that net zero solar powered living is not only possible, but it's economical. And when those two things collide, why wouldn't you do it? So anyway, let's go ahead and get started. Rather than have my picture on the screen and you'll see me squinting trying to read some of the text, here's a picture of me. I'm the old guy. I have the pleasure of working with Ben Newell and Alex Long, 2 younger guys, and we're the principals of our company, Build Equinox. And our company is a manufacturer of a smart ventilation system we call the Serve 2, our 2nd generation unit. It's manufactured here in Urbana, Illinois, and shipped throughout the U.S. as well as Canada. And it's a smart ventilation system that you can learn more about either from our website or from looking at some of the webinar and other materials that we've written on its performance. But basically, as a smart ventilation system, it brings in fresh air when you need it. It doesn't when you do not. And its mission in life is to keep us healthy and doing that in a very energy efficient manner. Our driving mission and mantra here is basically, in the words of Aldo Leopold, how do we live on a piece of land without spoiling it? And so our company, an engineering-based company, is dedicated toward finding solutions that allow us to live in a healthy, comfortable, and sustainable manner. And among those things, maintaining our health, cognition, helping us sleep better, helping us be more productive. These things have much, much more value, and we'll touch upon briefly, than the cost of energy. Energy is actually a very cheap commodity. It's plentiful. We just need to be able to use it in a sustainable manner. To me, the simplest way to explain why this is important, it's the future generation. These 2 grandchildren of mine who are now almost 3 years old and running much faster than me these days, you just have to look at their faces to see we just have to do better to leave them a better life, to provide opportunity for future generations. And we also need to recognize that when we do things efficiently, it does not mean that anyone throughout the world has to do without in order for a fraction of the population to do with. That there are enough resources available when we operate in an efficient manner so that throughout the world we can improve life, the quality of life. I'm like a broken record, and some of you who are signed in have known me for quite a while, and my poor wife has to hear this day after day for nearly 50 years now, but all I've ever worked on has been living on renewable energy from graduate school in the 1970s, where you see a picture of me taking a picture of myself in a heliostat mirror at Sandia National Laboratory, to when I ended my academic career at the University of Illinois as an advisor for the 2007 Solar Decathlon team. The other gray-haired picture, the other gray-haired in the Solar Decathlon picture was my colleague, Mike McCulley, who an architecture faculty member, and I'll mention him again in this talk. And when I arrived at Illinois in 1980, the University of Illinois, I started the Solar Energy Laboratory. At that time, solar thermal energy collection looked like it would be an important piece of the puzzle for the residential sector, but now that's not the case. Solar photovoltaics coupled with heat pumps are the answer, are the economical answer and the energy efficiency answer for powering our homes. And so this talk will concentrate on solar photovoltaics as far as a net zero energy home. A little bit of history, a lot of the hard work's already been done, and so we're really just at the lower edge of what's needed to improve a house a bit more, regardless of the climate throughout North America, for example. But back in the 1920s, when we didn't insulate homes, when they were very leaky, a lot of that because the way we cooked, because of the way we heated with fireplaces, that we needed to have a lot of ventilation flowing through. And windows didn't fit well, they were single pane. If you kept the house of 1920 era all heated, it would use an enormous amount of energy. Here showing about 150,000 kilowatt hours a year, maybe $15,000, $20,000 a year energy bill with today's prices. But that house, you didn't keep it all warm. You didn't keep it all comfortable. There was no air conditioning in the summer. And in the wintertime, you kept the parlor warm during the day. You maybe added some heated water or some heated rocks to your bedroom. You didn't have comfort throughout the house. You wore clothing, heavy clothing, as well as perhaps jackets and coats in your house during the winter. Moving to the 1950s, as central heating systems were developed, still not much in the way of air conditioning, but sealing a house up better, adding some insulation in the walls, adding storm windows, that we significantly dropped the amount of energy used by a house. And then moving to, I look at 2010 as kind of the beginning of high performance homes, where we see quite a few of them, versus conventional homes. So 2010 C is conventional, 2010 S super performing. And you see there's not a big difference in energy between these two, but they are significantly different. With the drop in energy, which from the one level to the other, the conventional to the super, it is a significant drop in energy. But when you look at where we were in 1920 or 1950, it's not that big of a drop in energy. But some of the other significant features, respiratory illnesses more than doubled over 30 years, from 1960s, 70s, and 80s up to 2000. And the other change, the amount of energy that humans use in a home, televisions, computers, air conditioning, that we have other things we're using electricity for that we didn't in the past. And so as we move to a high performance home, one of the more significant changes in the high performance home is that it is dominated by people loads. The conventional home of today also knows when people are in it, but not as significantly as when you reach the level of performance that we'll be talking about with a net zero energy home. That's in contrast to the house of 1950s or 20s, didn't even know if you were home or not. Like a car of the 1950s, 2 tons of metal. If there was a person riding in it, it hardly knew it. But today's much lighter cars, more efficient cars, they do know when you load it up with people. Now, today's high performance home, when you couple that with effective fresh air ventilation, and this means smart ventilation, in which you actively sense the air quality and bring fresh air in when you need it, and then minimize the infiltration when you don't need it, that this is also a much healthier home than the homes that are being built predominantly. Just a brief, and you'll find a lot more literature on health and productivity in our other reports and writings and presentations, but if all 100 million or so homes in the US with roughly 325, 350 million people were efficient homes, and there's a lot of work to get there, but the energy they would use per year would be about $160 billion per year, about half that for people, about half that for climate. If we compare that to the costs of getting sick from the flu or from colds, or what asthma currently costs us spread over the populace in the United States, and then even more so what poor air quality, which is pervasive in our homes, and it is a myth that a leaky home is a healthy home, that it has good air quality. Where the leaks occur and where you live are two different things, and our research, our field research, absolutely shows that where you live in a house, even if it is a very leaky house, that most likely that room where you're sleeping or you spend the most time in, the air quality is not good. Where it's good is in the laundry room or in the mechanical room or in the basement or somewhere else that has a significant amount of leakage. But when we look at these dollar numbers, and there's many, many other, from hay fever to other allergy costs that we see an increasing prevalence of, we see that this far outweighs what we spend on energy per home. And the big dog in this list, cognition, now that we are getting more quantitative measures on how poor air quality impairs our creativeness, our focus, our ability to understand information, that just a 5 to 10% drop of human productivity is well over $1 trillion a year. And we've done this to ourselves. If we've sealed up homes to make them more energy efficient and then not worked to add additional fresh air in an energy efficient manner. This plot that shows the indoor particulate concentration, the same is also true of indoor volatile organic compounds, these gases that are just emitted from cooking, furnishings, human odors, that we see that these are 10 times greater than what they used to be, say 1920 and before, when homes were quite leaky. And when we layer on a plot of how asthma has increased in our populace in the United States, since those records have been kept in the 1970s, we see that this trend layers on, maps out in direct proportion with that. And while we don't understand the direct cause, I think this correlation is very strong and indicating the importance of getting fresh air to keep ourselves healthy, and that these costs are every bit as significant as the energy costs that we'll talk about in this. Now, one of the problems that we find as we do workshops and training sessions on designing homes is that it's complicated and it's hard to figure out where to start. Some people will tell you that, well, just start working on the house, make it very well insulated and sealed, and don't worry about the other stuff. Do that first, independent of all the other things. But that is absolutely the wrong approach. The house is a system, in order to economically optimize it, you must consider all the factors simultaneously. The type of water heater you put in, the type of appliances, the type of windows, the amount of insulation, the type of heating and cooling system. All of these things impact the optimization process. A house with electric resistance heating will have, when it's economically optimized, a different level of insulation thickness than a house that uses a heat pump. Why? Electric resistance heaters typically cost much less than a heat pump. A 1-ton mini split heat pump that many of you may be familiar with costs about $2,000 these days, while electric resistance heater, you can buy a similar capacity heater for maybe 20 bucks at Walmart. So the cost of that heater is different, but then you get 3 times as much heat per unit of electricity with the heat pump as you do with an electric resistance heater. So that efficiency of the heat pump relative to its cost, relative to the cost to insulate and manage the energy flow through your house walls and roof, all of these things need to be put together in order to find the economic optimum. And so as we follow through the steps in this talk, I'm trying to give you some direction so that you can step by step move through and handle the simultaneous nature of this problem. So here's the 7 steps that we're going to be looking at. And these steps are something that we've simulated in our Zeros modeling program, which stands for Zero Energy Residential Optimization Software. And I'll talk a little bit more about Zeros. It's free software that we've developed over several years, and it's free to use. But these steps, regardless of using Zeros or some other, whether REM rate, PHPP, Energy Plus, you can follow these same steps with any other software. The 7 steps, in order to have some perspective of where we're starting, and then as we end up with our net zero house, we're going to start with a conventional house. And because windows are kind of, say, a complex feature between letting heat pass in and out through the window from winter to summer, as well as the radiation effect. Let's look at what a house would do with no windows, and then if we covered the south facade of the house with windows. And then the real answer is somewhere in between those, but we'll keep those in mind so we see energy performance wise as well as dollar wise. And I think some of you may be surprised, as many folks have in mind that windows are economic benefits to a home. We'll tend to show you that they are not, even in a northern climate where they can be. And in southern climates, they absolutely tend to be negative energy performance as well as economic performers. But windows are very important, and so that doesn't mean to not have windows. Then as we move through our cases, we're going to move to sealing a house, but as we seal a house, we'll add a smart ventilation system, and we'll look at the costs as well as the performance changes as we go from conventional to that. Then we'll add a heat pump water heater from an electric water heater and look at, this is such a substantial part of the energy usage in a high performance home, and the difference between a heat pump water heater and an electric water heater. It's a significant aspect of gaining high performance efficiency. And then moving on, let's increase the insulation until it's no longer economically feasible. At some point, diminishing returns on energy as you insulate more and more, that the cost of that insulation will not be paid for over the lifetime of the house by the insulation thickness. That's going to be different throughout the country, but the answer is not, say, a very sharp answer. It's not a very sharp peak as far as an optimization. And so you can be kind of sloppy about whether you use 8 inches or 12 inches. And we'll talk about what that means as far as that aspect. As we move through those, then we'll add solar in and look at how that compares to not having solar. And so in effect, you're going to put in your own power plant to power your house. And we'll look at a range of costs. Today, I think most of you around North America can install or have installed a solar photovoltaic system for about $3 a watt. Now, just a few years ago, when Equinox House was built, almost 10 years ago, it was about $4.50 a watt. And with the 30% tax credit, US federal tax credit, that brought it down to about $3 per watt. But today's system, we're seeing people have systems installed for $3 per watt. But in order to contrast that with, say, $2 a watt, we'll look at what I call case A here, where you might either picture that as a $3 per watt installation with about 30% tax credit to get you to $2, or that we are well on our way toward $2 per watt installed solar PV systems. And that will give us some perspective on how that impacts the life cycle costs, how that impacts the financing, the monthly expense. And then, because it's a very important aspect of our own living expenses, we'll look at transportation costs, both in terms of how much solar it takes to drive. We'll just assume 12,000 miles of EV transportation, and then how that impacts the overall economic picture for a house. And I hope you'll be pleasantly surprised that it says, get an electric car and put in enough solar to drive that. And if you do these other things to build a house so that it's net zero energy, your house is going to use less energy than today's conventional house, as well as provide you with 12,000 miles of driving per year. My house, what we call Equinox House, we'll look at a few features of it, but the name Equinox House, this uprising overhang on the 612 pitch roof where the clear story windows are, on the Equinox, and within 2 weeks of the equinox, that overhang edge goes from, in the spring, from allowing full solar radiation, direct solar radiation into the main living area and master bedroom area of the house, to totally excluding the direct sunlight. And the direct sunlight is about 85% of solar radiation on a clear day. That 15% blue sky light that comes in during from the spring equinox to the fall equinox, when the direct sunlight's excluded, that's more than enough to daylight the inside of this house, and to make it so that you can comfortably read throughout those rooms in the house. This house has less than 10% window to floor area. It is one of the best daylit homes, if not the best daylit home I've ever lived in, as well as walk through. And it does it without glare. It does it without, frying you somewhere in the house. It's just very comfortably daylit. The home's modern look was by Gene Ascoli, a wonderful architect who actually worked for Taliesin Associated Architects, Frank Lloyd Wright's firm, and I'm a fan of Frank Lloyd Wright. And this house that my wife and I had built, it's meant to be a modern take on the Usonian home. Hidden entrance inside, large public open space, and then a private area of the house for bedrooms. And one of the comments, whether you picture this house as a sleek, say, Porsche design of a house or a chicken coop, that's for others to argue about. But my feeling is that you can have form and function together. And this dumpster, which happened to be in Asheville, North Carolina, I think is a good example of that. Here's something holding trash. It's one of the most beautiful dumpsters I've ever seen. Just looking around Equinox, it is a simple 2,100 square foot ranch, but looks can be deceiving as you look at the Equinox shading, as I just mentioned, and you can see here it's during the summertime when no direct sunlight's coming into any of the south-facing windows, and this is a significant drop in air conditioning capacity requirements. During the wintertime, when the sun is low enough to come in the clear stories, we get more than just the sunlight impinging on the windows, incident on the windows. That uplifting overhang and the 212 pitch on the lower act as a solar concentrator, and so we get about 2 to 3 times as much solar energy into those windows as what's hitting directly the window area. That 612 pitch on the north-facing slope of the house, that white roof not only keeps the house cooler in the summer, but it reflects over to our solar collectors, which are on a berm in the backyard. And while it's a secondary effect, we get almost 15% additional solar energy collection, essentially for free, just by a little bit extra head scratching and analysis. This house is also the first home in Illinois that was approved by the State Department of Plumbing, State Department of Public Health, for allowing rainwater to be used within a municipality within the home. And in our case, we're allowed to use it for toilets and garden watering, but the system is designed to be used for showers and laundry, which we'll do at that time when the state's more comfortable with rainwater usage. And as someone who grew up in a rural area and relied on rainwater to fill our cistern, I can tell you it's the best water in the world to shower and wash clothes with. The Styrus japonicus tree that's out front, that's also called a Japanese snowbell. And that's also another tip of our hat to Frank Lloyd Wright for the Asian influence in his architecture, which is more noticeable in his prairie style homes. But also this is a relative to a tree that produced resin that was the origin of styrofoam, of styrene, and then polystyrene polymer. And this house is insulated with SIP, structural insulated panels, but indicating that as we're getting smarter and better, that perhaps we'll be able to return more to bio-based materials for a number of things that actually did have its origin in biomaterials, but now is more petroleum based. And as I mentioned, we have 10%, 2,100 square foot house, 180 square feet of windows, and the house is wonderfully daylit. And then we have as much north-facing window as we have south-facing window, and that's because our gardens and the direction we want to look is to the backyard. Now, what I'm telling you and the steps that we're following, I'd like to say that we're innovative and this is new, but you can go back to the 1970s, and at the University of Illinois, we had the University of Illinois Small Homes Council and Building Research Council developed what was called the Illinois Locale House. This is really the origin of many other super insulated homes to come, such as the Passive House, which as you look at their archive material, you'll see that this was definitely a house that they referenced. And what we're going to model looks very similar to this simple ranch home, about a 50-foot by 40-foot, 2,000 square foot home as we move through these steps. This is a locale house in reality. This is in Urbana and was built in the 1970s by my colleague, Michael McCulley. And he designed this house. And just a couple of years ago, I stopped by and talked to the residents who just thoroughly love the home and have loved very, very low utility bills ever since they've lived in it. Now, I mentioned that windows are not economical, and that's true throughout North America. But if you built a home like this, which also happened to be in North Carolina, like the Frank Lloyd Wright dumpster, this might be, from an engineering viewpoint, the economic optimum, that it would save you money, but it probably doesn't have as big of a pool of people who would be interested in buying it. Aesthetics are important. Our expectations in what we would like in a home. We do like to see out. We do like daylight in a home, and those things are important for us. And so even though a window may not turn out to be good from an economic balance, just like many other things that we buy, it's something that we like, and we should be able to have it if we can afford it and if we want it. And I also want to make the point that Equinox House looks the way it does, not because of energy, but because of my wife and I enjoying a modern look. And so as we worked with our architect to develop that look, that's the main reason, not the energy features around it. The house across the street, it's also about a 2,000 square foot ranch. If you look at the floor plan, if you just take the shell of the house off, it looks very, very similar to our house. And it could be just as good of a performer. Absolutely, it could have the same performance. But when you don't pay attention to how a house is sealed, when you allow folks to come in and drill your internal framing into Swiss cheese as they run electricity and plumbing and ductwork through the house, you're not going to end up with that performance. And then just a word on electric vehicles as we go into the results of this. There's a lot of good things that will happen as we move to electric vehicles. It's happening throughout the world. This picture of these two cars in Amsterdam, any car charger you walk past in Amsterdam is going to have a couple of cars plugged in. And the sculpture that was that's in Rotterdam showing the misery of oil, that there's been a lot of costs associated with oil that we've had to bear, and a lot of benefits as we move over to electric transportation. And as I mentioned, moving to electric vehicles, it's going to, with a high performance home, it's going to use less energy than what our current conventional homes use without the transportation. In 2012, we bought our first electric car, this Ford Focus, which now has about 35,000 miles on it. We get put about 5,000 miles or so a year on this car, and then our other, which is a plug-in hybrid, another 2,000 to 3,000 miles on that. We're fortunate to live in a town where you just don't drive very much. But this car we bought in New York. When they first came out, you could only get them in New York and California. And so we went to New York, visited some relatives, and then as a Gen 1 electric vehicle, plugged in about every 60 miles from New York all the way back to Illinois. And we stopped at the factory in Michigan on our way back. And because of some former students of mine who are on the electric vehicle platform at Ford, contacted the plant management. They charged up our car and gave us a nice tour of the plant. And then we were on our way. One of the unrecognized features of an electric car is that solar-powered electric transportation costs about 2 to 3 cents per mile relative to gasoline in a 30 mile per gallon vehicle which will cost you about 10 to 12 cents per mile. Gasoline is never going to drop to a price that can compete with solar-powered electric transportation. And the cost of the vehicles for this car costs about $40,000 at the time. Now moving down to about a $30,000 cost. That just like flat screen TVs, it's going to be less expensive than the thousands of parts that are in an internal combustion engine. And as a native Detroiter, I think this is going to be good for our industry and our overall economy, as well as our pocketbook economy. The solar system for Equinox House is an 8 kilowatt system. And just a couple things on that. It costs about $4.50 a watt to put it in then. Now you can put it in for $3 a watt. And if you're a do-it-yourselfer, you can do it for $1.50 a watt. This 8 kilowatt system, about 700 square feet. It produces about 10,000 kilowatt hours a year, about 8,000 for the house, and about 2,000 for the car. And the current generations of electric vehicles, you get about 3 to 4 miles per kilowatt hour. So 2,000 kilowatt hours is going to give us about 6,000 to 8,000 miles of driving a year. And you can see roughly how that proportions over this photovoltaic system. I mentioned zeros, and in our sign up, there was a link to this web page. As I mentioned, it's free. Hit the subscribe and you can sign up. There's a lot of student classes, architectural and engineering classes around the country that are using this for zero energy house design modeling. It's very easy to get up and going on. And there's a PDF that follows through these 7 steps in more detail than this webinar, along with a CSV file that you can import into Zeros so that you can actually see all the details of the results that we're going to discuss, that we'll be discussing in a minute. And I also want to point out, we're not bothering you. You sign up for this, use the software, you're not going to hear from us, and no one else is going to be bothering you. The whole point of this software, it's what we use to design homes, and it's a great tool. We want to see more zero energy homes built. And so that's the purpose of Zero, but bringing together all of these facets, but in a simple to use manner. And our goal is to simplify, our goal is to save you time. So where it's more important that you spend time is out in the field, making sure the house gets built with the quality that you intend it to. As far as validation of these results, we've vetted this in many manners, from comparing to NREL's best test, where some different locations with different home variations have been modeled in what are considered to be the top models available, what's now called Energy Plus, but the old Doe and Blast models, as well as Seri Sun Code. Graduate student of mine, Luis Martinez, who finished his PhD in 2009, did the majority of the work on the computational engine as well as validation studies. And because I'm very proud of Luis, who's now a professor at Universidad Centroamericana in El Salvador, here's a recent picture from just a couple of weeks ago of Luis along with the US ambassador at the net zero energy building project that Luis has been leading at UCA, his university campus. That's a beautiful, gorgeous building that will provide them with lots of data and hopefully help start paving the way to a better future for El Salvador. Then finally, just simulation versus reality, just so you can use zeros with confidence. These blue dots are the average performance of 13 identical homes. These are manufactured homes, Vermont homes that were built in Vermont, and these are homes that are largely in Vermont. And these homes are averaged Throughout the year, with over 2 years of data collected, it takes a lot of time and a lot of data to be able to statistically average so that you can compare with a simulation model. And if we run zeros with 1 occupant versus 3 occupants, you can see that 3 occupants increases the energy usage. And the average of these 13 homes was about 2.5 occupants. And so you can see that very, very good agreement between the daily energy requirement in kilowatt hours per day versus outside temperature. And just looking at when it's 20 degrees out, one of these homes would use maybe 30 or so kilowatt hours per day. We're talking about $3 worth of energy, $3.50 worth of energy, the price of a cup of coffee. So these homes use very, very little energy, and we can predict it very, very accurately. I also, though, want to point out, and one of the problems when you look at comparisons between simulation models and data, this is what that data really looks like, all of these solid points. The yellow points are the simulation predictions. If I happen to compare the simulation to one of the very low energy usage homes, I might reach a different conclusion than if I used one of the homes that uses quite a bit more energy. And so all of those data points are what were averaged at a particular level of temperature to give the previous plot. And in perspective, those open circles that go up sky high, these performance values are for conventional homes, just showing you how much more energy they use than these Vermont homes, which are net zero energy buildings. So the range of people usage in these homes is very significant, as we mentioned, and on average, zeros can predict it. This is one of the main output sheets on zeros, and not to go through much detail on it, but I do want to point out on the life cycle cost. So this is for the conventional home that we're starting with about $412,000 of life cycle costs. That's the cost of the house, which is estimated at about $213,000. $200,000 of that is the base cost, or estimated to be $100 per square foot cost, which is typical for our area. And then the things related to the energy performance of the house, the cost of insulation, the cost of heating, cooling, ventilation, equipment, and utilities are the other factors that add up to the life cycle costs, along with then replacement of, say, for example, the heating and cooling system every 25 years, that would be replaced over a 100-year lifetime. The red and green arrows are direction arrows to help guide you to optimum levels of insulation thickness in the walls and the roof and window and hot water. Of course, the less hot water you use, the better. The less electricity people use, the better. The fewer occupants, the better. The thicker the wall, the less energy, but at some point, the higher the life cycle cost. And then other output results related to the heating cooling capacity of the system. And here, for example, with the heating system for this conventional house, and then with no windows, we see that the heating on a sunny day and on a cloudy day, the heating capacity is exactly the same. As you start adding windows, that will change. And the cooling system capacity is exactly the same. And as you add windows, that will definitely change. And then finally, some things over on air quality related to the airflow for this conventional house, which has an assumed 7 ACH, air changes per hour, blower door level. So typical of what you'd see with conventional construction around the country, that this is going to lead to, on average, about 800 parts per million of carbon dioxide. But as I mentioned, the average is not typical of where you're living and where you're sleeping. We generally find that to be much, much higher. And you need a managed distribution system to ensure it's fresh air where you live in your home. And then finally, the bottom line, this home would use about 12,000 kilowatt hours of electricity. We assume a heat pump, a high performance heat pump in this house. You can explore different options and put in those parameters. Quite a bit of dehumidification needed for our area. You can see that is actually quite a bit relative to the air conditioning energy. The air conditioning energy at 97 kilowatt hours is not much, but as soon as you put windows in, I assure you that's going to go up quite a bit. And you can see that the people loads and hot water loads, that these are roughly a third of the overall loads relative to the climatic loads for the house. So let's look at these results, and so these cases are laid out, and as you use those cases with zeros, you should find these same numbers, and for sure contact me anytime for any questions related to them. But first, starting with a conventional home with no windows, as we just saw on that sheet, we'd use about 12,000 kilowatt hours of electricity, this blue bar. And if we put windows on the south side of that house, which would be 500 square feet of good Energy Star windows, not super windows, but good performing windows, we can see that the energy usage would drop a bit below 12,000 kilowatt hours, but not by a substantial amount, especially for adding 25% windows to the south. And so the reality for, say, a house with 12% windows will be somewhere between those two. As we seal the house up and then add a smart ventilation system, there is a significant drop, almost 2,000 kilowatt hours just by sealing this house up better. As we add a heat pump water heater instead of an electric resistance heater, and I think I forgot to mention that we have 3 occupants assumed in the house. That's about 50 gallons of hot water per day of usage. And by putting in a heat pump water heater, we see a similar nearly 2,000 kilowatt hour drop of energy per year. Now, 2,000 kilowatt hours of energy is about 6,000 to 8,000 miles of driving in an electric vehicle. So sealing the house up, putting in smart ventilation, putting in a heat pump water heater instead of electric resistance heater, we've dropped enough in energy to essentially use that for our annual driving needs. And then finally, our conventional home assumed 6 inches of wall insulation, 12 inches of ceiling or attic insulation. If we optimize that, and in going through zeros and adding an inch by inch additional thickness of insulation, and the costs that I've assumed that are built into the data are about $5 per cubic foot for wall insulation and $2 per cubic foot for ceiling insulation. And the difference being that wall insulation may need some additional structure or effort in order to get into the walls or to build walls that can hold additional thickness, where ceiling or attic insulation, you can just blow additional insulation on top of it. And for these costs and the assumed costs of electricity in this area, we'd find that the wall thickness should be at optimum about 11, 12 inches, and that the ceiling insulation would be thicker because it's less expensive insulation, and it would top out at about 19 inches. As we look at the economics, though, as I was talking about, it's not a real sharp optimum. So 8 inches of insulation, 14 inches of insulation relative maybe an optimum of 10 to 11. isn't that big of a deal. You'll just be buying a little more or a little less solar panel in order to compensate for the wall insulation. As we go to putting in photovoltaics, it doesn't impact, so cases 6 and 7 do not impact the energy performance, but over on the right-hand side, we see that in case 6, where we're just meeting the house electric needs, we're going to match that with a solar system, and we'll look at its characteristics. And if we also want to add about 12,000 miles of driving, we would put in about 3 kilowatts of solar PV, which would give us close to 4,000 extra kilowatt hours per year, and that would be about 12,000 miles of driving. If we look at the house costs, our conventional home, figuring it would be $100 per square foot, and I know you folks in California and New York and elsewhere and other metropolitan areas are saying, we can't build a house like that. Well, it just scales, but this base house, whether it's $200,000 or $600,000 for the base house without any energy features, that does not impact the optimal house solution. So that is just a reference cost, and all the energy related items then vary on top of that. The insulation thickness relative to the climate, relative to the cost of electricity and solar panels. The main thing to notice here, between a windowed house and a non-windowed house, there's a significant cost difference. I've assumed $45 a square foot, and for good Energy Star windows, you might find those, say, $30 to $60 a square foot. Super windows, maybe $50 to $100 per square foot, things that are reaching like R6, R8 type thermal insulation value. And so there's a significant cost difference due to windows. And as I mentioned, pick what you need for the views you want, for the look that you want, and the aesthetics. And as we look at life cycle costs, you'll be able to see the impact due to those aesthetic preferences. As we look at the cost of sealing the house, that goes up not because of the cost to seal a house. If you're smart about it and build with quality, it should be getting well sealed along the way. Our recent newsletter article on the aero barrier technology provides you some additional new views at how to seal a house in what should be a pretty cost efficient manner. The main cost jump is for the smart ventilation system, about $5,000 to add that on top of the conventional house. When you add a heat pump water heater, add another $1,000. Regular water heater, maybe $400 to $500. New heat pump water heater at a big box store, maybe $1,000, $1,100, without any tax credits or things like that assumed or to be dependent on. When you add additional insulation to the walls and to the ceiling, as I mentioned, adding, going from 6-inch wall to about 11-inch wall, along with a ceiling insulation that went from 12 inches to 19 inches, that this added maybe another somewhere in the range of $8,000 to the house cost. And then adding solar. If it's $3 per watt versus $2 per watt, now 6A where I have $3 per watt, that's then with an assumed 30% tax credit, taking it down to $2 per watt. And so basically between the green and the blue bar, we're looking at $3 a watt and $2 a watt installed solar cost. And then adding an additional 3 kilowatts for transportation, you can see that our house cost, what you're going to amortize, if it's written into the cost of the house, is going to increase relative to that. When we look at the utility costs, starting with the conventional house, as I mentioned, windows can reduce utility costs in northern climates. It's just that it does not reduce it enough to pay for the costs of the windows. And then these are south-facing windows, so east, west, north windows are not going to have this utility benefit. But as we look at the change of utility costs going to a sealed home with smart ventilation, we see a substantial drop in utility. Going to the heat pump water heater, another similar substantial drop. Optimizing the insulation thickness, another significant drop. And then adding solar to make us net zero. Now, the reason that doesn't take us to zero utility costs is that I've assumed a $20 per month customer service fee. So we're not getting off the grid, we're staying part of the social fabric of the community and contributing excess energy when we have it and then drawing from the grid when we need it. As we then add additional solar for transportation, though, we do go negative because, as I mentioned, solar-powered electric vehicles cost 2 to 3 cents per mile relative to a good-performing gasoline engine car, a 30-mile-per-gallon car, costing about 12 to 13 cents per mile. So when your mileage shifts over to solar-powered electric, that then you now have an actual dollar savings in your pocket over the course of the year. When we look at 100-year life cycle cost, on the conventional cases, we see a significant difference between no windows and windows, and the reality where a 25% windowed home is quite a bit, but let's say 10 to 12%, that will be somewhere in the middle on the annual life cycle costs. And this assumed a replacement of the windows about twice over the lifetime of the house. And so that's additional economic information you can enter into zeros. As we go to the sealed house with smart ventilation, we see a life cycle cost about the same as the conventional house. But remember that the sealed and smart ventilated house truly has good air quality, where the conventional leaky house is not good air quality. The stuff blowing through the walls of the house to provide you with supposedly fresh air is not as good as the fresh filtered air coming through a smart ventilation system. And as we mentioned, where you live and where the fresh air is blowing into your house, those are two different things. So these are significantly different cases, even though they look to be similar economically. And as we add a heat pump water heater, we insulate the house, we add solar, we continue to see the life cycle costs drop. And finally, with the last case in there, $3 per watt solar with enough for 12,000 miles of driving, but a $2 per watt installed cost with a 30% tax credit. We see that we keep stair-stepping our way toward a more and more economical house. But we also want to know, even though the house may have the best life cycle costs, best lifetime costs, what's it going to cost us per month to have this net zero home with solar powered transportation? And looking at our conventional home and the mortgage, taxes, insurance, utility, and within those zeros data sheets, you'll be able to see what I've assumed for insurance and tax, about $600 a year for insurance, for example, and then a tax rate that's typical of our community, which isn't that inexpensive as far as taxes, but you can see how that is coupled with those costs, and then the utility costs. But basically you see that the solar powered house with transportation, whether you have $3 per watt or $2 per watt installed solar costs, that it's within $50 of the conventional house. And the solar powered house is much more is much better air quality. It's a much healthier house, as well as being much more stable as far as future costs, not relying on low escalation of utility prices. And the windowed house, the amortization of the windows does add a substantial increase to that house cost. As I mentioned, carbon dioxide, even though it appears low for the conventional house with a 7 ACH infiltration, and in sealing the house to like passive house levels of 0.6 ACH, the smart ventilated home distributes fresh air to where people are, where the leaky, haphazardly ventilated home does not. As far as solar PV area, we're talking a fraction of the roof space, more typically having solar added to a roof, so about 500 to maybe 700 square feet, depending on if it's just powering the house or powering the transportation. The extra 200 square feet for powering 12,000 miles of driving, you could also think of as basically being about the area of the garage space that the cars are going to be kept in. And we're talking solar systems in the range of about 6 to 9 kilowatts, under the 10 kilowatt level that several utilities throughout the country consider to be the maximum they would allow on a residence. Without going into the details of the latent side, but Zeros also does accurate modeling of humidity in the winter and summer. And in the summer, this home would be removing about 25 liters per day, both due to the humid nature of our Illinois climate, as well as what humans add into their activities and respiration. In wintertime, we would be adding in about 5 liters per day to not go below 20% relative humidity. And when we look at heating and cooling capacity, we see that there's not a large change in terms of what's needed for heating. Somewhere between 4 and 6 kilowatts under a design day, a very, very cold extreme day for heating, except for the heavily windowed house on a cloudy day. Windows, even good performing windows, are not as good as a well-insulated wall. And when the sun's not shining, you definitely have a deficit and a significant increase in the needed heating capacity, along with other discomfort of just that cool surface radiating to you. And similarly, in the summertime, that the cooling capacity is not significantly different between the conventional home without windows and then these high performance homes, somewhere in the range of 1 to 2 kilowatts, which would be somewhat less than a ton of cooling, where windows definitely impact on a sunny day in the summer. If the windows are not direct solar protected, the cooling capacity you're going to need to keep people comfortable. And one other comment as far as heating and cooling capacity, and this will, we're at the end here, and I apologize for going over. We're in an era where, as I mentioned, humans are significant factors in the energy used within a house. And in an analogous manner to old cars versus today's car, an old car running at highway speeds had more than enough power because of the inefficiency of that vehicle, the weight of the vehicle, the drag coefficient of that car, that when it needed to accelerate from zero during city driving, stop-start type driving, it had more than enough power inherent in it for driving at highway speed to reasonably accelerate up to the speed you'd like to go. But newer cars, being lighter weight, being much more efficient, and drivetrain being much more aerodynamically designed, if you only put in the power needed to drive at average speeds, you would not have enough power to reasonably accelerate to where you would be happy with the car, as well as other people riding with you or other people driving behind you, would be likely to go into road rage as you barely creep up to highway speed. So there's an amount of power needed in a car just for it to reasonably accelerate, and that now is typically greater than what's needed just to keep the car running at a steady speed. Today's homes are similar. So when you use manual J or other methods to look at the capacity of the heating and cooling system, when you would go to the winter design temperature, often what's called 99% or 99.6% design day, a day that's extremely cold in the winter, much colder than the average, say, January temperature. In yesteryear's home with this red line that's steeply sloped, that heating requirement was so much more than what people have as a preference for moving a house from one temperature to another, that was enough for sizing the heating and cooling system. So what I'm trying to show between that steep red line and the dashed red line is that if you move from that design day condition over to the average winter temperature, the capacity that went with that design day was greater than what would also be needed for people's preferences, what we often call 3 sigma design. But you take the general populace, you go 3 sigma out in variations, the temperature people would like in their home, how much they move the temperature up and down, and you would find that you have enough capacity to accelerate the house in temperature to get up to a temperature or drop down in temperature, whether you're in summer or winter. When you go to today's home, that shallower sloping red line in the winter, and you look at the design day temperature and you draw that over to the average winter temperature, you're going to see that you no longer have enough heating capacity in the winter or cooling capacity in the summer that you're going to meet a large fraction of the populace preferences for heating and cooling. So we've entered an era where we need heating and cooling capacity just to meet the variation of people's preferences. And if you design heating capacity and cooling capacity based on the average preference, you better get ready for a lot of callbacks, because half the population may be fine with average design because their heating and cooling preferences are below that, and the other half is greater than that. And you're not going to have enough capacity if you think that the average heating and cooling prediction capacity is enough to meet the general populace demands. Think of it like designing a doorway. Doorways are what, 78 inches tall? That covers 3 sigma, or about 99.7% of the populace in height. If you instead design doorways at 5'7", the average height of people in North America, you would find that, well, anybody less than 5'7" is happy, and anybody greater than 5'7" in height is a little bit annoyed. And that's what will happen if you use average design day data in a high performance home. Now, to account for this human comfort preference variation, statistical analysis is needed, and that data I showed that looked like a shotgun hit it, we've used that data in order to find that this human comfort preference is about 1/3 of a ton. So as you're thinking you may need a candle or 1/10 of a ton or something like that, you should start thinking that the minimum need is about 1/3 of a ton. And then with your design day heating or cooling, if that adds another 1/3 or so of a ton, at minimum, you're going to need about 1/2 of a ton to a 1 ton capacity system on heating or cooling. Now, one of the strange things with today's high performance variable speed mini split, as well as geothermal heat pumps, and you can read this in our June 2018 newsletter that explains it more fully. 2 1-ton mini split heat pumps operate more efficiently at a half ton. 2 1-ton mini splits operating at a half ton are more efficient than a single 1-ton mini split operating at full capacity. So while people have a fear of overcapacity and inefficiency, that is absolutely not true with today's mini splits. That 2 mini splits operating at half capacity are more efficient than a single mini split operating at full capacity. There's no ifs, ands, or doubts about it. This is from real data, real laboratory experimentation. So don't be fearful about adding $2,000 for a 1-ton mini split to a house. It's going to operate great at partial load. It's going to be 1% of your house costs if your house costs $200,000. And so do that, and you're going to reduce callbacks due to comfort issues. I'm just going to say that this 4,500 square foot Morton building is net zero powered. If this building that I'm talking to you from can be net zero powered, surely the homes that you're working on can be as well. Took a little elbow grease, some insulation, some solar, some LED lighting, some improved windows, but there's absolutely no doubt that here from this data in February 2016 to 2017, we ended up with a net positive 500 kilowatt hours. So we can do this. We can do this throughout the country. Our weather here in Illinois is some of the worst in the country because we get hot, humid weather from Houston and New Orleans coming up in the summer, and we got Arctic blast from Minnesota coming down in the winter. These new technologies, the low temperature air source heat pumps, geothermal heat pumps, new ways to economically seal, and then the new era of smart ventilation, hybrid water heaters and clothes dryers, optimize insulation and solar PV. And if you have to cut down trees, don't buy into community solar or community wind farms in order to have renewable energy. But you're going to lower your energy usage and have a healthier home. You're going to have a lower life cycle costs than with conventional construction. Your monthly expenses are essentially going to look the same. And if you don't believe me, run it in zeros and then call us anytime to discuss. And for sure, I thank you, and I feel our grandchildren will thank you for those efforts as well. Thank you very much for participating. Bye-bye.